Hey guys, today we're going to be doing just a quick review of the Life on the Edge activity we've been working on for the past few days that dealt with electron shells and valence electrons. So this whole concept of the electron shell originated with Niels Bohr, who is actually a scientist we studied earlier when we talked about the different models of the atom. So in the Bohr model, you would see a nucleus in the center with the protons and the neutrons, and then around the outside where the electrons were, Bohr proposed that they would be found in these different shells around the nucleus. Another word that he used for this instead of shells, you could say that they were found in different energy levels as well. So it's okay for you to call it, an electron shell or energy levels for these different electrons, as long as you understand that they're on kind of different levels out here. So as far as the notation, each level he gave this letter n and he called it the quantum number. So the letter n equals 1 means I'm in kind of the first layer here. N equals 2, I'm in the second layer here. N equals 3, I'm in the third layer here. So the next step of this was that every shell could hold a specific maximum number of electrons. So there's a point where each shell becomes full. And so each shell, as you go outward, can hold more and more electrons. The first shell, n equals 1, can hold 2 different electrons. All right, n equals 2, the second shell out can actually hold 8 electrons. N equals 3 can hold 18, you go to 4, it's 32. And actually, if you want to use a formula to predict this, the formula that you use to figure out how many each shell can hold is 2n to the second power, and n is just our energy level. So for the first one, in the first energy level, 2 times the first energy level squared equals 1 squared is 1 times 2 is 2. So I get my 2 electrons here. For the second energy level, 2 to the second is 4. 2 to the second is 4 times 2 gives me 8. And so I see that I have 8 electrons here as well. So I can work that all the way to the top. This fifth one, since it says it's unknown, let's just work it out. 2 times 5 to the second power equals 5 squared is 25 times 2 gives me 50. So actually, in my fifth energy level, or in my fifth shell, I can hold 50 electrons. Not anything that you'll actually be tested on, but just kind of interesting to see how you can figure out the number of electrons in each shell. Now, as far as how these electrons are situated, or giving a title to these specific electron shells, we came across this idea of a valence or a core electron. So those are the two different things. In the outermost shell, that is called the valence shell. All right, so the outside shell here, the one that's all the way on the outside, is our valence shell, and that contains our little valence electrons. So the valence electrons are just the ones that are on the outside shell, just that outside ring. Okay, so in this atom here, we have 2 valence electrons, because on that outer shell, there's only 2 electrons. Every other electron in the atom is considered to be core electrons. So in this case, again, we only really have one other layer here, so there's going to be 2 core electrons. But let's go back actually to our model over here. Let's say this had 4 shells. So all of these electrons on the 4th shell would be my valence, and then all the other ones combined would be my core. So I'd have to add the shell 3, shell 2, shell 1 all together as the core electrons in that case. So it can change depending on how many shells your electron has, or your atom has. When we want to go ahead and predict the valence electrons and the core electrons, we can use the periodic table as a really helpful tool. So not only is it helpful in determining, metals versus nonmetals, it's not only helpful in, looking at the atomic number to see the protons and the electrons and all those things, but we can use the organization of the table to predict, number one, how many different shells of electrons are there going to be, and number two, how many valence electrons exist for a certain element. So we'll stay here for just 1 second. If I'm looking across the top, I see that each of my columns is given a number. And when we colored ours, we wanted to make sure we did this in a separate color on the right-hand side and the left-hand side, these numbers, because that ones digit is going to communicate how many valence electrons my atom is going to have. So in the first column, every single element in this first column is going to have one valence electron. Everything in the second column will have two valence electrons. Everything in my 13th column, or in some cases we'll see it labeled as 3A, they're all going to have three valence electrons. And so you see that the column number is very useful in predicting how many electrons an element has in its outermost shell. Now, as far as determining how many shells it's going to have, the rule we came up with was whatever row we are in. Now remember, rows that go left to right, across, right? Whatever row we are in, that'll communicate how many electron shells there are. So if I'm in the first row, that means there's one shell. If I'm in the second row, that means there's going to be two shells. 3 shells for the third row, 4 shells for the fourth row, 5, 6, and 7. And so if I was to ask you, for selenium, how many shells does selenium have? Well, I'd have to go over here, right? And I'd see, oh, it's in the fourth row. So I should have 4 electron shells, or 4 energy levels. If I asked you how many valence electrons it would have, you would have to go up the column, right? And see that the ones digit is a 6. So this is going to have 6 valence electrons. All right? So let's just practice one more time. How many valence electrons does phosphorus have? So we're going to locate phosphorus first. Find phosphorus right here. Phosphorus happens to be in the 15th column. Now remember, the ones digit is the one that tells us how many electrons or valence electrons it has. So phosphorus actually has 5 valence electrons, because it's in the 15th column. How many core electrons does phosphorus have? Well, this is going to be kind of a second step to this. We haven't solved a problem like this before. But remember that we know the atomic number at the top of the box tells us if I have 15 protons, right? Well, if I have 15 protons, then I need to have 15 electrons to cancel them out. So I want the core electrons only. I just want the ones in the middle. So I have to get rid of these valence electrons on the outside. The core electrons don't count those. So if I started off with 15 total electrons and I took away my 5 valence electrons, then I end up with a sum, or I guess a difference here, of 10 electrons. Which means that in terms of core electrons, I have 10 core electrons. Elements with the same number of valence electrons have similar chemistry, and they're always located in the same group. So we saw that when we just examined the columns here. All these things in column 1 have the same amount of valence electrons. All these things in column 2 have the same number of valence electrons. So the same group is the same as the same column. And we discussed actually earlier in this marking period how they have similar chemistry, because we looked at a whole mess of these alkali metals. So we looked at lithium and sodium and potassium and rubidium, and there was this video we watched where we put each of these things into water, and we saw as we go down from one to the next, right, the reactions got more and more violent. By the time we got to cesium, when they put that in water, the entire container exploded. So we saw that the similarity in their chemistry was just that they all react in water. And as we go down this column, it actually becomes more violent. But we want to focus on the fact that they just react. They all react and have that in common. So I hope this was a helpful recap. I hope that you were able to get all the answers for your guided notes, and we will see you next time.